Hi and welcome back. We're still doing some example videos on electrostatics, and this question actually follows up from a previous question. When the previous question we calculated the charge after R that used to be, I think it was +8, and S used to be -4. After they came in contact, we worked out the net charge on each of them, and that would just be the average of these two, which is 8 minus 4, which is 4 divided by 2, which is a +2 charge. So R and S has now +2 microcoulomb charges. Okay, so +2 microcoulomb, sorry, my mu is wrong on this side, microcoulomb charges. Okay, and this question now follows up. After R and S have been in contact and separated, a third sphere T with a charge of +1 microcoulomb is now placed between them as shown in the diagram below. Draw a free body diagram to show the electrostatic forces experienced by sphere T due to R and S. And so free body diagram would just be like this. Here's my sphere T. Then we have an attractive or positive, well, let's see. It has a positive charge. Both of these have positive charges. So in other words, T would experience a repulsive force from S. They have the same these two have the same charges, but T is closer to R and further away from S. So in other words, the repulsive force experienced by T from S will be smaller than the repulsive force he would experience from, so let's call this FR. That force would be stronger than the repulsive force he's experiencing from S, Fs. So this is point T. Okay, does that make sense? Both are repelling him because they have same charges. Calculate the net electrostatic force experienced by T due to Rs. Okay, so obviously we have that the force experienced by T, okay, the net force, let's just call it the net force, is equal to, and so let's choose the direction where with the bigger force as positive. So we're going to choose that as positive. So we'll calculate the force experienced by T with R, and then we'll subtract the force experienced by T with S. Why do we subtract it? Because they are in opposite directions. So very important. The force calculation is quite simple. We take K Q R times QT because we're working out the force experienced by those two. Okay, and the distance between RT squared minus, then we'll take the force K Q S QT. This would be the formula to calculate R squared ST, to calculate the force experienced if it was only due to S, and if it was only due to R would have been the first force. Okay, so now simply substitute. K is 9 times 10 to the power of 9. The force experienced by R is a +2, and it's microcoulomb. So do remember to use 10 to the power of -6. We have to work in coulombs. Times T is 1 times 10 to the power of -6, and then divided by R. Now this is also important. R must be in meters, and here we have that the distance between RT is 10 centimeters. So in other words, we must change that to meters. 10 centimeters is 0,1 meters, and that's squared minus, now same thing, 9 times 10 to the power of 9 times 2 times 10 to the power of -6, because that's the charge on S, and 1 times 10 to the power of -6, that's the charge on T, and then divided by R squared, which in this case is 20 centimeters. 20 centimeters is 0.2 squared. And so let's calculate that. Gives us 9 times 10 to the power of 9 times 2 times 10 to the power of 6 times 1 times 10 to the power of 6 is equal, that's the numerator, this first numerator, divided by the denominator, which is 0.1 squared, is equal to 1.8 newtons, so 1,8 newtons. The second part is the same that we had before. I should have actually stored that value, but that's okay. Let's do it again. 9 times 10 to the power of 9 times 2 times 10 to the power of 6, negative 6 times 1 times 10 to the power of 6 is equal to 0.18 divided this time by 0.2 squared. Okay, equals 0.45 minus 0.45 newtons. So we have an answer of 1.35 newtons. And then because it's a force and it's a net force, the net force will be in the direction. Remember we said that the force exerted by R is larger only because it is further away from S. So the force they exert the same force, R and S, okay, but the closer that I come to R, the stronger the force would be. So in other words, this at the point where T is, at this point, T will experience a force, a net force towards S, or away from R. Okay, so the next question, define electric field at a point. An electric field at a point is a region in space where a charge will experience a force. There we go. Calculate the magnitude of the net electric field at the location of T due to R and S. Now, there's two ways of doing it. This is actually very easy once we've done our first one. Is all we could do is take the electric field equal to force divided by Q. So all we need to do is substitute the force that we've calculated in the previous question, that is our 1.35 newtons, divided by the charge of the particle experiencing that force, and that would be this particle here. In this case it's T, which is 1 microcoulomb, so 1 times 10 to the power of negative 6, which gives me an answer of 1.35, and the 10 to the power of negative 6 becomes 10 to the power of positive 6 force per coulomb, Newton per coulomb, Newton per coulomb. That would be the electric field. Easiest 3 marks you would get in this paper. Well, thank you very much for watching. I hope you enjoyed this video and this topic. We'll see you in the next video. Bye.